Very difficult spelling. He's silent here. Okay. Riemann Stieltjes integral. He's silent. Sometimes you can call it RS integral. Very much analog. Analog to what we developed. Instead, what is the key difference between Riemann Stieltjes and Riemann integral? So this integral, when you compute integral with respect to this line element interval, you call that basically as Riemann integral. So if you compute the integral of one function with respect to some other function, you call that as Riemann Stieltjes integral. Okay. So why I am interested in this? Because when I am doing this, I am also doing this. Just by taking g of x to be
dx
equal to
dx
just equal to x. Just take g of x as x. So whatever results which are true for this are true for this. Okay. This is what the key difference is. That's what I'm interested in. So if you can do things generally, so that's generally. So let alpha is a monotonically increasing function. Monotonic and increasing on A to B. Yeah. I tell you that monotonic increasing functions which are defined on closed interval must be bounded. Because it's like that kind of a thing. Monotonically increasing. So A is somewhere here and B is somewhere here. And that's where alpha of A and that's where alpha of B. So the function is also bounded at. What is that bounded? It's bounded between alpha of A and alpha of B. Shouldn't be a problem. Okay. And so what actually we want to do? We want to do that, okay, take this interval A to B and take a monotonically increasing function, something like that, roughly. Okay. And I have another function defined on the same interval F. Now I want to integrate this f with respect to this function alpha. So in other words, rather than partitioning A to B, I'm going to partition roughly this alpha basically. And I'm going to do things with respect to this alpha. But it's going to be really analog what you did previously.
area between area between curves.
Yeah.
Area between
that's what it's done. Let P is a partition, just like x naught, xn of the interval a to b. Okay. And I am defining what we call delta alpha I, this notion delta alpha I, as alpha of xi minus alpha of xi minus 1. Take a subinterval xi minus 1. And delta alpha is basically what alpha xi minus alpha xi minus 1. Pretty bit simple. Now, I would like to define UFP, but with respect to this alpha. So, what do you think? What should be the definition of upper Riemann sum? This should be sum, okay, of capital MIs, okay, where MIs are what? The maximum value, okay, over the subinterval xi minus 1, right? Obviously, multiplied by multiplied by
You alpha, you basically F P alpha.
u.
F.
So upper sum of f with respect to the partition V, okay, over with partition V, and you want to compute this upper sum with respect to alpha, or with respect to increments in alpha. So here you have alpha. So in other words, instead of xi minus 1, now you have alpha of xi minus alpha of xi minus 1. Agree? So, and then P alpha is going to be the sum of Mi and delta alpha I. Obviously, I runs from 1 to n. I runs from Agree? Okay. So I can say that, explicitly mention what is Mi? Mi is the infimum of values of f of x when x is between xi minus 1 and x. Difference is just you're multiplying with the increments of. Then similarly, capital Mi is the supremum of. Same as this. So what do you think that what should be the definition of this upper Riemann sum with respect to d alpha? Give me the definition.
Summations.
Hmm?
Summation, sir.
Mission.
नहीं sir, integral.
So it's an infimum. So it's infimum of upper Riemann sums. Okay, where B the partition of AB. Okay? And similarly, it's going to be F with respect to the alpha. This Riemann supremum of lower Riemann Stieltjes sum. Partition of okay, this is going to be the case. And what would be then the Riemann Stieltjes integral? Should be same as, we're going to say that f is Riemann, is integrable in Riemann Stieltjes sense. Okay, if these two guys exist and both equal. We say that this integral, Riemann Stieltjes integral of f(x) is if these two guys exist and both are equal. It's just really an addition of what we did at. Okay. Pretty much similar. We can also prove, not going to repeat the argument, because the argument is essentially saying that the properties that we proved about lower Riemann sums and upper Riemann sums previously are also true here. Okay? They're also true here. In other words, if I have two partitions P and B star of the interval A to B such that P is contained in P star, in other words, P star is the refinement of P, then P alpha should be less than or equal to, and then P star alpha, and we have we have P alpha should be bigger than or equal to P star alpha. Exactly. If I expect that, the argument is going to be 100% same as the previous proof. Just replace xi and xi by alpha of xi and alpha of xi. That's it. Just replace that. So the proof is going to be precisely same, nothing. No trouble left. Okay? So that's it. I guess we can continue from next. So we're going to do all theory of integration in terms of Riemann Stieltjes. You need to do it from Rudin.